High Bandwidth Memory 3, HBM3. HBM stands for High Bandwidth Memory and is a type of memory interface used in 3D, stacked DRAM, dynamic random access memory, in some AMD GPUs, aka graphics cards, as well as the server, high-performance computing, HPC, and networking and client space. Samsung and SK Hynix make HBM chips. Ultimately, HBM is meant to offer much higher bandwidth, lower power consumption compared to the GDDR memory used in most of today's best graphics cards for gaming. The global hybrid memory cube and high bandwidth memory market was valued at $906.5 million in 2022 and is projected to reach $3,054 million by 2029, at a CAGR of 18.9% during the forecast period. The global key manufacturers of hybrid memory cube and high bandwidth memory include Micron Technology, Samsung Electronics, SK Hynix, Advanced Micro Devices, Intel, Fujitsu, IBM, Xilinx, and Nvidia, etc. in 2022. Here, we outline the key benefits of HBM3. Increased storage capacity. HBM3 supports up to 32 gigabits of density and up to a 16 high stack, resulting in a maximum of 64 gigabyte storage. This is almost a 3x growth compared to HBM2E, providing more memory for advanced applications. Faster data transfer rates. With a top speed of 6.4 gigabits per second, HBM3 is almost double the speed of HBM2E, 3.6 gigabits per second. The market may see a second generation of HBM3 devices in the not-too-distant future. One need only look at the speed history of HBM2/2E, DDR5, 6400 megabits per second upgraded to 8400 megabits per second, and LPDDR5 maxing out at 6400 megabits per second and quickly giving way to LPDDR5X operating at 8533 megabits per second. HBM3 above 6.4 gigabits per second is within reason. Improved power efficiency. HBM2E already offers the lowest energy per bit transferred, largely due to being an unterminated interface, but HBM3 substantially improves on HBM2E. HBM3 decreases the core voltage to 1.1 V compared to HBM2E's 1.2 V core voltage. In addition to the 100 MV core supply drop, HBM3 reduces the I/O signaling down to 400 MV from HBM2E's 1.2 V. Enhanced channel architecture. HBM3 has kept the overall interface size the same for the HBM DRAMs, 1024 bits of data. However, this 1024-bit interface is now divided into 16 64-bit channels, or more importantly, 32 32-bit pseudo-channels. Since the width of the pseudo-channels has been reduced to 4 bytes, the burst length of accesses to the memory have increased to 8 beats, maintaining a 32-byte packet size for memory accesses. Doubling the number of pseudo-channels will be a performance improvement over HBM2E. Combined with the increase in data rate, HBM3 can provide a substantial increase in performance over HBM2E. Advanced RAS features. HBM3 introduces several improvements to its reliability, availability, and serviceability, RAS, capabilities, including on-die error correcting code, ECC. HBM3 DRAM devices also support error check and scrub, ECS, when the device is in self-refresh mode or when the host issues a refresh all bank command. The results of the ECS operation may be obtained by accessing ECC transparency registers via the IEEE Standard 1500 Test Access Port, TAP. The HBM3 standard's new RAS feature supports refresh management, RFM, or adaptive refresh management, ARFM. New clocking architecture. HBM3 changes the clocking architecture by decoupling the traditional clock signal from the host to the device and the data strobe signals. In fact, while the new maximum rate of WDQS and RDQS in HBM3 is 3.2 GHz to enable a data transfer rate of up to 6.4 gigabits per second, the fastest rate the CK will run from the host to the device is only 1.6 GHz, even when the data channels are operating at 6.4 gigabits per second. Decoupling the clock signal from the strobes allows the clock signal to run significantly slower than the data strobes. The maximum transfer rate of information on the CA bus is now 3.2 gigabits per second since the CA clock has been capped at a maximum rate of 1.6 GHz. While HBM2E requires a CA transfer rate of 3.6 gigabits per second, HBM3 only requires a command and address, CA, transfer rate of 3.2 gigabits per second. High-speed internal clocking. The new HBM3 clocking architecture enables the user to keep focus on a low latency, High-performance solution when migrating from HBM2E to HBM3. The highest defined frequency for the CA bus with HBM3 is 1.6 GHz while the data strobes operate at 3.2 GHz. This enables users to implement a DFI 1:1:2 frequency ratio for an HBM3 controller and PHY. In this case, the controller, DFI, PHY, and memory clock all run at 1.6 GHz while the strobe frequency is 3.2 GHz. This gives designers a DFI 1:1 frequency ratio for the CA interface and a DFI 1:2 frequency ratio for the data, all of which minimize latency.